roughly 1 month from now, the interstellar object designated 3I/Atlas will move to the far side of the Sun relative to Earth, rendering it temporarily unobservable by ground-based and near-Earth space telescopes. This geometrical constraint marks a natural pause point in our observational campaign and makes the present moment ideal for synthesizing what has been learned so far about this remarkable visitor from interstellar space. Of particular interest is an upcoming close encounter on October 3, 2025, when 3I/Atlas will pass within approximately 29 million kilometers of Mars. During this flyby, the high-resolution imaging science experiment, HiRISE, camera aboard the Mars Reconnaissance Orbiter will have an opportunity to image the object at an effective pixel resolution of roughly 30 kilometers. While this resolution will not allow surface features to be resolved, it may still provide valuable constraints on the object's brightness, morphology, and immediate environment, complementing the observations already obtained from Earth-orbiting space observatories. One of the most striking results to date comes from high-resolution imaging conducted by the Hubble Space Telescope on July 21, 2025. These observations revealed that 3I/Atlas does not exhibit a conventional cometary tail. Instead of the familiar structure produced by dust particles streaming away from the Sun under the influence of solar radiation pressure, the Hubble image shows only a diffuse, roughly symmetric glow of scattered sunlight. Crucially, this glow does not extend preferentially in the anti-solar direction, where a dust tail would normally be expected. Nor does it show significant elongation perpendicular to the Sun-object axis. The only detectable asymmetry is a slight elongation toward the Sun itself, sometimes described as an anti-tail orientation, which is inconsistent with dust being pushed away by radiation pressure. If the scattered light were dominated by dust grains with sizes comparable to the wavelength of visible light, roughly half a micrometer, those particles would be efficiently accelerated away from the Sun and would form a tail extending several arc-seconds behind the object. Such a feature would have been trivially detectable by Hubble. Its absence strongly suggests that 3I/Atlas is not releasing significant quantities of submicron dust particles into space. This conclusion has profound implications for the nature of the object. In typical comets, the observed brightness is often dominated by sunlight scattered off dust in the coma and tail rather than direct reflection from the nucleus itself. For 3I/Atlas, however, the lack of a dust tail indicates that most of the detected light must originate directly from its solid surface. Spectroscopic observations reinforce this interpretation. The spectrum of 3I/Atlas shows substantial reddening, meaning that its reflectance increases toward longer wavelengths. In the absence of fine dust grains, this reddening must be intrinsic to the surface material rather than a property of an extended dust cloud. Such reddening is not unusual for bodies that have spent long periods in cold, radiation-rich environments. Kuiper belt objects within our own solar system, such as the contact binary Arakoth visited by the New Horizons spacecraft, display similar spectral slopes. In those cases, prolonged exposure to cosmic rays and ultraviolet radiation is thought to chemically process surface ices and organics, producing complex, carbon-rich residues that impart a red coloration. The similarity suggests that 3I/Atlas has experienced a comparable irradiation history in interstellar space over billions of years. If the light we see is indeed reflected primarily from the surface of 3I/Atlas, then its observed brightness can be used to estimate its physical size, provided an assumption is made about its reflectivity, or albedo. For an albedo of approximately 5%, which is typical of dark, primitive bodies in the Kuiper belt, the observed brightness implies a surface diameter of roughly 20 kilometers. This already places 3I/Atlas among the larger known small bodies in the solar system and makes it vastly larger than the first 2 interstellar objects ever detected, 1I/Oumuamua and 2I/Borisov. However, this estimate may be conservative. Independent measurements from the SphereX Space Observatory complicate the picture significantly. SphereX detected thermal emission from 3I/Atlas at a wavelength of about 1 micrometer during observations conducted between August 8 and August 12, 2025. Interpreting this flux as originating from the object's nucleus suggests an even larger size, corresponding to a diameter of approximately 46 kilometers. If this value is correct, then 3I/Atlas is not merely large by interstellar standards, but enormous, with a mass roughly 1 million times greater than that of 2I/Borisov. Such a disparity is surprising and difficult to reconcile with existing models of interstellar object populations. If objects the size of Borisov are common enough to be detected, then vastly larger objects like 3I/Atlas should be exceedingly rare. The fact that we appear to have detected such a massive interstellar body after only a decade of systematic surveys by the Atlas telescope raises serious questions about our understanding of the abundance and size distribution of rocky and icy material in interstellar space. Indeed, previous theoretical estimates suggest that the amount of rocky material per unit volume in interstellar space is far too small to make the detection of a 46-kilometer object within such a short time span likely. In my first paper on 3I/Atlas, I showed that the inferred density of interstellar solids would need to be larger by a factor of roughly 10,000 to account for the delivery of a single object of this size into the inner solar system over the duration of the Atlas survey. This discrepancy points either to a fundamental flaw in our population models or to the possibility that 3I/Atlas is not a typical natural fragment ejected from a planetary system. Further insights come from SphereX imaging, which shows 3I/Atlas as a point source with no detectable dust coma or tail, consistent with the Hubble observations. However, SphereX did detect a cloud of carbon dioxide gas surrounding the object, extending out to distances of at least 348,000 kilometers. The inferred mass loss rate of CO2 is approximately 70 kilograms per second, indicating that some level of volatile outgassing is occurring. Interestingly, no corresponding cloud of water vapor was detected. The observations place an upper limit of about 4.5 kilograms per second on the water mass loss rate, which is an order of magnitude lower than earlier claims that suggested water outgassing at rates of roughly 40 kilograms per second. Those early claims now appear to have been spurious, as previously argued, and the SphereX data provides strong evidence against significant water activity. The absence of a bright water gas coma is particularly puzzling because 3I/Atlas was located at a heliocentric distance of about 2.5 astronomical units during the SphereX observations, placing it near the solar system's so-called water ice line. At this distance, water ice on the surfaces of typical comets begins to sublimate vigorously. The fact that 3I/Atlas shows substantial CO2 outgassing but little to no water activity suggests an unusual composition or thermal history. One possibility is that water ice is buried beneath an insulating surface layer that suppresses sublimation, while more volatile species, like CO2, can escape from greater depths. Alternatively, the object may be intrinsically depleted in water relative to carbon dioxide, reflecting formation conditions in a very different stellar environment. Taken together, these observations paint a picture of 3I/Atlas as an object that defies easy classification. It behaves neither like a typical comet nor like a purely inert asteroid. Its large inferred size, lack of dust production, strong surface reddening, selective volatile outgassing, and apparent improbability under standard population models all point toward a body that challenges our assumptions about interstellar debris. As it disappears behind the Sun and later reemerges, and as data from the Mars flyby are analyzed, 3I/Atlas will continue to test the boundaries of our understanding of planetary system formation, evolution, and the material that drifts between the stars.